We're going to now begin using energy to actually do some problem solving. So there's a few things we want to think about when we are using energy to do problem solving. And really the key is we're going to focus on the transfer of energy. Okay, similar to what we were doing with those energy bar charts, except now we're going to do it in equation form. So we want to think about what kind of energy does the object start with. That's the first question we want to ask. What energy does it end with, all right, at some later point in time? Okay, and is there any work being done by non-conservative forces? All right, and we're going to bring that all together using our equation. It's essentially the same idea as what we were doing with the energy bar charts, but now we're going to use this equation. The one thing you want to keep in mind is we do want to be careful with the sign of our work. Make sure that the sign of your work makes sense logically. If it's gaining energy, we should have positive work, and if it's losing energy, there should be negative work. So here's the first practice problem, and the first thing I'm actually going to do, we have this nice diagram here, is I'm going to go ahead and think about what kind of energy I have at each of these points in time. So initially we have a spring being compressed at point A here, so I'm going to start with US, our spring potential energy. It then goes up to a height where it momentarily comes to rest here at point B, so that's going to be gravitational potential. Now there is some kinetic in between. We're going to find out in a second that that actually doesn't matter. And then we get to the end here at point C, and we have a height, so we're going to have gravitational potential, and we are moving, so we also have kinetic. So for that first question, we want to calculate the height at point B. I'm going to start with my conservation of energy equation. E initial plus work equals E final. And I'm going to go ahead and fill in the things that I know. This is going to be similar to our F equals ma equations, where you have to fill in the specific energies that exist at various points in time. So we're starting here with US, spring potential energy. That's the only energy we have initially. There is no work being done, so I'm just going to skip that part. And the energy we end with at point B here is gravitational potential energy. So I've plugged in the formulas I know for each of those, for spring potential energy and gravitational potential energy, and now we can go ahead and plug in the values I know. My spring constant is 600. X, the distance the spring is stretched, is 28 centimeters, or 0.28 meters, okay? And that's going to be equal to my mass, which I know is 1.2 times 9.8 times my height. And when I go ahead and solve for that height there, I get 2 meters as my height. For the second question, I want to know the velocity at point C. So once again, I'm going to think about my conservation of energy equation. E initial plus work equals E final. And for this one, I'm going to just think about going from point B to point C. There are a few different ways of doing this, and I'll actually show you a different way in a second. But if I'm thinking about going from point B, I'm starting with gravitational potential energy at point B. There's no work being done. And I end with gravitational potential and kinetic at point C. So I can go ahead and fill in those formulas once again for gravitational potential energy and kinetic energy. The one thing I'm going to do is I'm going to say this is HI, my initial height at point B, and this is HF, my final height at point C. I now can plug in what I know, so 1.2 times 9.8 times 2 equals 1.2 times 9.8 times 1 plus 1/2 times my mass, which is 1.2, times v squared, and when I solve for v, I get an answer here of 4.43 meters per second. So that's going to be my velocity at point A. I also could have set this up considering the period from A all the way to C, okay? And so for that, I would have said that I start with spring potential energy, and that just becomes gravitational potential and kinetic. So we're going from point A here all the way to point C. All right. Whereas with this one, I just went from point B to point C. Either one is valid because as long as we account for all the energy that an object has at one point in time, in this case point A, and all the energy it has at a later point in time, point C, and we account for any work done in between, which in this case was 0, okay, this equation is going to work, right? So as long as you account for all the initial energy, all the final energy, and any work done in between, it doesn't matter what 2 points in time you pick. For the last part of this problem here, we're asked to draw an energy bar chart showing the energy at these various points. So I'm going to start here. I have spring potential energy at point A, Okay, that's the only energy I have because we're not moving. Going from A to B, there's no work being done because there's no non-conservative forces, and so all of that energy that was spring potential energy at A becomes gravitational potential at B. Once again, no work done between B and C, and what I'm left with is half as much gravitational potential energy, and I know that because my height here was 2 meters, and my height here is 1, so I'll say it's 2 bars of gravitational potential, and the rest has become kinetic. For this next one, we have a situation where there's a ramp, okay, that has a length here of 4 meters, and it's sloped at an angle of 30 degrees, and we're going to put a box here with a mass of 5 kilograms at the top of that ramp. All right, and it's going to slide down the ramp, and as it's sliding down, there's a frictional force opposing its motion of 10 newtons. So energy-wise, I want to think about what kind of energy we start with, what kind of energy we end with. So we're starting up here with gravitational potential energy because we have some height. We don't know what it is, but we do have some height above the ground. We're ending here with kinetic, okay, because we're moving and we no longer have a height. And there is some work done by friction that's happening in between. So I'm going to go ahead and think about my conservation of energy equation here, E initial plus work equals E final. So that initial gravitational potential energy plus the work done by friction, I realize that work will ultimately be negative, but the cosine of theta term will take care of that. So I'm just going to add in the work done by friction even though that work has a negative value. And that's going to be equal to my final kinetic energy. So I can go ahead and fill in the formulas I have for potential energy, work, and kinetic energy, and then start filling the values I know. So I know my mass here is 5, G is 9.8. My height I don't know, but I can think about this triangle here. We have a 4-meter long ramp sloped at an angle of 30 degrees, and so this height here is just the opposite side. So I can say that height is just going to be 4 times sine of 30, which gives me a height of 2 meters. So I can fill in that height there. I'm then going to add the work done by friction, so that's going to be the force of friction, which is 10, times my displacement, which is 4, and I'm using that full distance because friction acts as that box slides that entire displacement, so the displacement should be 4, not 2. My angle here is going to be 180 degrees because as I'm traveling down the ramp like this, friction is going up the ramp in the complete opposite direction. Okay, so the angle between my force and my displacement is 180 degrees. And that's going to be equal to 1/2 times my mass here times v squared. So I go ahead and I solve that left side, and I end up getting 58 as my number there. Keep in mind you should be in degrees mode, and that's going to be equal to 2.5 v squared, and so I find that my velocity here is 4.8 meters per second. Okay, we move on to the next problem here, and it looks identical to the last one because it is. However, this time we want to re-solve this problem using forces and kinematics. Now, this is something that I'm not always going to make you do, but I do want to make a point here as we're starting to introduce energy that there are multiple ways of doing these problems. And on a test or a quiz, I'm not going to take off. You could, depending on which way you solve it. You could solve it either way, but I do want to make a point here about the difference between the two methods. So with forces, of course, we want to set up our free body diagram. So thinking about that, we have our normal force going up at an angle like that. We have the force of gravity going straight down, and then we have the x and y components of that gravitational force, Fg cosine theta perpendicular to the plane, Fg sine theta parallel to the plane. And we have our force of friction going back up the ramp. From there, I'm going to go ahead and set up my max and my may. So in the x direction, I have this Fg sine of theta minus that force of friction, and that's going to be equal to my mass, which is 5 times a. Okay, and so I can sub in here for Fg 5 times 9.8 times sine of 30 minus that force of friction, which is just 10, equals 5a, and so we get that my acceleration here is 2.9 meters per second squared in the x direction. In this case, I actually don't need the y forces, so I can just ignore doing may here and go ahead and use kinematics now to solve for the speed. So I'm going to go ahead and set up my chart for kinematics. I know my displacement is 4 meters. I'm starting from rest, and I just found that my acceleration is 2.9 meters per second squared. We want to know that final velocity, so we're going to go ahead and use our VF squared equation. So I could go ahead and plug in here for the values I have for the acceleration, which is 2.9, and for that displacement of 4. And I can go ahead and solve for VF, and I get an answer here of 4.8 meters per second, which is the same answer I got using energy. So let's talk about this idea for a second. We just did the exact same problem 2 different ways, one time using energy, one time using forces and kinematics. Both of them are okay, both of them are physically correct, both of them are valid. However, my advice to you, it is almost always easier to solve for things using energy. And this problem wasn't that bad, dealing with forces and kinematics, but I still think even this problem was easier using that first method with energy. There's less work involved typically. Okay, no pun intended there. But I think it's almost always easier to solve using energy. There are 2 major situations when we can't use energy. The first is time. Okay, energy doesn't take into account the time piece of any of these. So if you need to know something about the time, you're going to have to use forces and kinematics. The other one is when you're solving for things at angles. Okay, energy is a scalar. When we want to know angles, like for projectile motion, for example, okay, we can't use energy because energy is just going to output another scalar answer. All right, and it's not going to allow us to determine the direction that something's moving or accelerating or things like that. So those are the 2 big situations when you really can't use energy. But in most other situations, if you can use energy, I would suggest trying to use energy. Okay, for this next one here, we have an algebraic one that we're going to set up once again with conservation of energy. So I'm going to start by identifying the types of energy I have at various points. So we start up here at the top of the ramp, and we're going to have gravitational potential energy, of course, because we have a height. This box then is going to slide down the ramp frictionlessly until it reaches this little patch here, where there is some friction, and then it's going to continue on. So when it goes through that patch, all right, it's going to have kinetic energy. And we know that during this period of time, we do have some work being done by friction. So our energy equation here, E initial plus work equals E final, is going to be UG plus that work done by friction, and that's going to be equal to our final kinetic energy. So I can go ahead and fill in the formulas I know for gravitational potential energy, work, and kinetic energy. The other thing I need to do is I'm given this coefficient of friction here, and I'm going to ultimately need my frictional force to find my work. So what I'm going to do is I'm going to set up all the forces acting on the object as it's sliding across that patch. So I have the normal force going up, gravity going down, and the force of friction going to the right. I know that that force of friction, which is what I'm looking for, is equal to mu times my normal force. And if I think about my y forces, I have no acceleration in the y direction, so that means that Fn minus Fg equals 0. And so my normal force is just equal to mg, which I can then use to get an expression for my force of friction. My force of friction is just going to be mu times m times g. That helps me for 2 reasons. Number 1, I now have mu in there, which was a variable I was given. And in a second, that's going to allow us to cancel out mass. So going back to our energy equation, I have mgh for my gravitational potential energy plus the force of friction here, which is mu mg, times my displacement, which is just this x here, so times x, times cosine of 180, because as this object here slides to the right across that surface, we're going to have a force of friction going to the left, and so that angle between my displacement and my force of friction is 180 degrees. So that's why it's cosine of 180. And that's equal to 1/2 mv squared. I can cancel out those mass terms there. And so what I'm left with is GH plus mu gx times -1 is equal to 1/2 v squared. And then I can multiply both sides by 2 and square root this to get that v is equal to the square root of 2gh minus 2gx. If I wanted to simplify it some, I could also say v is equal to the square root of 2g times h minus x. That would work as well, but you don't necessarily have to simplify it there. Either one is acceptable. We have another algebraic one here, so this time we have a car that is coasting along at a speed of v, and it goes up a hill to some height before eventually coming to a stop after reaching a height of h. So thinking about the energy we have, we're going to start here with kinetic energy because we're moving, and we're going to end with gravitational potential. So we can go ahead and set up our basic energy equation, and then we'll go from there. So I'm going to have kinetic, no work being done here because we're ignoring frictional forces, is going to be equal to gravitational potential. So 1/2 mv squared equals mg h. And before I even get into this problem, I can cancel out those m's, and what I'm left with is 1/2 v squared equals gh. So a relatively simple equation there. So the first question asks here what would happen if the initial velocity were doubled. So this is one of those situations where we're going to set up our new and our original. So we think about our original situation, that's just the equation we derived there. In our new situation, I'm going to go from this equation. I'm not going all the way back to the start, but I'm going to say 1/2 times 2v squared, that quantity, equals g times h prime, my new height. Okay, squaring that 2, I have 1/2 times 4v squared equals gh prime. And what I'm going to do in this case is I'm going to pull this 4 out in front. So 4 times 1/2 v squared equals gh prime, and I can just substitute in this expression here. So 4gh equals gh prime, which means that my new height is simply 4 times my original height. As always, if you can make the jump here and see that velocity squared is proportional to height, so if you double the velocity, the height increases by a factor of 2 squared, or 4, you certainly are more than welcome to justify that rather than doing this derivation. Situation B, we are doubling the mass. However, if we look at this expression here, the mass canceled out. Okay, so the mass doesn't matter. So this would be a case where there is no change because that height does not depend on the mass. So our new height would simply be h. For this last one here, we're going to change the acceleration due to gravity. So my new setup is going to be 1/2 v squared, that hasn't changed, equals g over 3 now, because it's 1/3 as much, times h prime. Okay, I see here that both of these are 1/2 mv squared, so I can just set them equal to each other. So I can say gh equals g over 3 times h prime. Those g's cancel out, and I can multiply both sides by 3 to find that my new height now would be 3 times that original height.